Hello everyone, I'm Srija Malyala and I'm a software engineer at AMD. I have Vaishnavi with me today.
Hi everyone, this is Vaishnavi working at AMD as a senior software developer.
We are here to talk about the advantages of the computational storage devices for storage applications. More specifically, the file system acceleration on the computational storage devices for efficient data storage. Let's jump right into it. As the agenda goes, we are going to first give an overview of the computation storage and a quick overview of the SmartSSD as we have used that computation storage drive. And then we are going to talk about ZFS, why we have picked up ZFS and which compression we have chosen to offload and why. Next, we'll discuss where we have modified the ZFS for offload. Later, we'll discuss the offload design and flow and how much and in what all aspects we have benefited. Let's get started. I'm sure everyone here knows what computational storage is, but let's quickly see an overview of its architecture. In the traditional system architecture, memory, CPU, and storage all had very defined purposes. However, with the increased system complexity and with the large amounts of data to be processed in the system, the current architecture shown to the left is showing some bottlenecks. These bottlenecks result from the higher CPU utilization for infrastructure tasks or from having to move large amount of data across the various components in the system. One solution to solve this problem is to move some of the computations closer to where the data resides, and that is the basic idea behind the computation storage architecture. SNIA defined computation storage as the architecture that provides computational storage functions coupled to storage, offloading host processing, or reducing data movement. There are three different types of the computational storage devices shown here. The one to the left is a traditional storage device where there is no accelerator. Followed by that is the computational storage processor where the FPGA drive fits in the SSD drive in the standard slots and communicates with the other SSDs over PCIe. To the right, we have computational storage array where the FPGA acts as an accelerator inline in between the CPU and SSD. In between, we have what is called the computational storage drive, where the accelerator is embedded within the SSD. Acceleration scales with the number of SSDs here. We have used the SmartSSD for the accelerator and storage. SmartSSD is a computational storage drive in the U.2 form factor with NVMe interface for storage access and FPGA as an accelerator. I'm sure you all know what FPGAs are. But for those who don't, FPGAs are the configurable architecture that can be optimized for any workload in milliseconds by simply uploading a bit stream. You all must have seen the advantages of FPGA for over a decade now, but the value of the FPGAs is even more pronounced with the computation storage. We see that the technology keeps changing. For example, for today, we have LZ4 and GZIP compressions, and tomorrow there might be a new compression algorithm. With FPGAs, you can always reconfigure and have a new hardware in no time. The storage is accessed using the standard NVMe interface, and the compute engines are accessed using the OpenCL interface here. Coming to the data flow, usually the data is read from the storage systems to the x86 RAM and then moved to the FPGA DDR for computation. And the result, the computed result, is copied back from the FPGA DDR to the x86 RAM. In the case of the huge data, this movement through the x86 RAM affects the overall system performance and efficiency. Now let's look at how an application running on the host CPU can make use of the SmartSSD to offload compute tasks. The first thing the application does is to trigger the DMA to move the input buffer into the FPGA DDR. It then triggers the compute engines in the FPGA. The compute engines process the input data and produce results in the output buffer, the buff2 located here in the FPGA DDR. Finally, the application triggers the NVMe interface to move the result buffer into the storage. This is a peer-to-peer data transfer, avoiding the host RAM. This is possible because of the 3-port PCIe switch implemented inside the FPGA. with its ports connected to the host CPU, NVMe SSD, and the FPGA. The entire FPGA DDR is exposed to the host via PCIe bar, allowing the host applications to allocate data buffers from the memory and inline data transfers directly to or from the SSD using the standard NVMe driver stack. So we have offloaded compression from ZFS. Let's see an overview of ZFS and why we have chosen ZFS in specific. ZFS is an advanced next-generation file system built with scalability, reliability, and performance in mind from the ground up. It also has many interesting features like the pooled storage, where multiple physical disks are combined into bigger storage pools, compression of data blocks before being written to the physical disk, snapshotting for recoveries from the crashes, or data integrity using the checksum for every block, and even redundancy and protection with the mirroring or RAID-Z configurations. Here are two different ZFS pool configurations. The one at the top is a mirrored pool configuration, and the one at the bottom is a RAID-Z2 configuration. The disk VDEFs at the bottom are the physical disks, and the ones at the top are the virtuals. Compression is always triggered at the top level VDEF. Compression in general can be offloaded mainly at three levels, like the application level, block level, and at the file system level. When offloaded at the application level, we can achieve the maximum efficacy as the application can control the buffer size to be compressed. But the con here is that we'll have to modify every application for offloading. Compression at the block layer in the Linux stack can provide the transparent compression without having the applications to modify. But the block size, which is typically the 4 KB at the block layer, renders the compression ratio to be less than desirable. The other issue is the overhead of triggering hardware offload for small blocks like 4 KB, which can bring down the overall CPU efficiency. The option of doing the compression at the file system level can provide an opportunity to achieve balance between the buffer size and the offload overhead. The file system level compression also provides transparent compression to applications to achieve the desired cost savings. The larger buffer size option also results in higher compression ratios. We therefore chose ZFS to offload the compression. Vaishnavi will now walk us through the offload design and flow.
Let us look at the ZFS write pipeline, which is triggered when the application writes data to the ZFS volume. As seen here, the data block is first compressed, optionally encrypted, and a checksum is calculated on it. Later in the pipeline, a disk write is triggered to write the data to the physical disk. I say disks here because the data block may be replicated in case of mirrored pools, or it is striped along with a parity data in case of RAID configurations. And here we have offloaded the compression to FPGA. Now, ZFS compression is supported with different compression algorithms, which user can choose at the time of pool creation. We have LZ4 and GZIP from level 1 to level 9. We have compared LZ4 and GZIP level 1 in terms of their compression ratios, throughput, and CPU resource utilization. As you can see here, LZ4 is efficient in terms of higher throughput and lower CPU utilization, but has a lower compression ratio. Whereas GZIP algorithm gives a better compression ratio, but consumes a lot of CPU resources and the throughput is also less. Every application today would want a lossless compression with a better compression ratio. Even though GZIP compared to LZ4 is giving us that, but it's coming at the expense of higher CPU resource utilization and a lower throughput. We can say that an ideal compression algorithm would be one where we can achieve good compression ratio with higher throughput and a lesser CPU resource utilization. So we chose GZIP algorithm for offloading. Now let's go back to the write pipeline and see how SmartSSD can be used to offload some of its stages. As seen here, we offloaded the compression and checksum calculation to FPGA kernels on the SmartSSD. Also, the compressed data is stored on the FPGA DDR, and this buffer is moved to NVMe storage directly during disk write stage of the pipeline. Now let's see an in-depth flow of how the compressed requests from ZFS are handled. The requests from ZFS are transferred to XSS. XSS is an intermediate kernel space library that provides higher level storage acceleration APIs to applications like ZFS. XSS in turn uses XRT APIs. XRT is a runtime library which provides APIs to discover the accelerated devices like SmartSSDs, load FPGA kernels, allocate memory in FPGA, execute compute kernels, and transfer data to or from FPGA DDR. First, a buffer object is created by XSS corresponding to the input data. This buffer is allocated in the FPGA DDR and mapped to the host buffer in ZFS. The input data is then transferred from the host memory to the FPGA DDR using a DMA. XSS allocates another buffer for the compressed data. This buffer only exists in the FPGA DDR because in the P2P flow, the data need not be moved back to the host. XSS then creates a command packet that specifies the addresses of input and output buffers and triggers the HLS GZIP compression kernel and then waits for the completion. Once the kernel finishes the operation, the compressed data is available in the output buffer. In the ZIO pipeline, after the compression, the compressed data is further processed for checksum calculation. In case of P2P flow, as the compressed data is in FPGA DDR, it is not ideal to compute checksum on compressed data by the host. Therefore, the default Fletcher-4 checksum algorithm used by ZFS is also offloaded to the FPGA. The checksum computation is done right after the GZIP compression. And then XSS reads the compressed size and 256-bit checksum information from FPGA DDR and passes it to the ZFS. Another factor which had to be considered while enabling P2P flow is the adaptive replacement cache in ZFS. ZFS by default has the cache enabled. So to support the default settings of ZFS, the compressed data in the FPGA DDR is moved to the cache by performing a DMA using XRT API. Note that this transfer of compressed data to the host is only to update the R, which is required for the read operations to find the recently used data in the cache. Finally, at the stage of writing the compressed data to the disk in ZIO pipeline, the compressed data is moved to SSD directly from the FPGA DDR. The GZIP compression algorithm used in this work is developed in high-level synthesis language using the Vitess software development platform. The design used to offload data compression to hardware in ZFS is multi-core GZIP compressed streaming kernel attached to the data mover kernel as shown in the figure. The data mover kernel reads the source buffer from FPGA DDR and writes to the input stream of the GZIP compressed kernel. Similarly, the data mover kernel reads the compressed data from the output stream of GZIP compressed kernel and writes to the P2P destination buffer present in FPGA DDR. There are 8 parallel engines of LV77, Huffman encoder, etc. inside the GZIP compressed kernel, which run simultaneously to improve performance. These kernels are designed in such a way that they can handle multiple compressed requests at once in pipeline fashion using a chaining interface. The kernels are also optimized at every layer internally, which makes them an ideal choice for this architecture. The overall resource utilization numbers for this design on SmartSSD platform are shown to the right. So now Srija will continue to explain about the test setup and the results we have achieved.
We have evaluated the value proposition of ZFS acceleration on SmartSSD using the test configuration shown here. We have created mirror pools, a common configuration used in ZFS. A mirror pool replicates the data written to one disk to other disks, thus providing the redundancy in case of failures. For example, if I write a chunk of data to the pool, the data is written to both the disks so that in case the data is lost from one of the disks for whatever reason, we will always have it stored in another disk. We have shown 2 disks per volume here, but we can have multiple disks to have more protection. In our test setup, we have used Dell 7525 AMD server, which is a dual socket with 64 CPUs. We have used Ubuntu 16.04 OS with 4.15 Linux kernel. And for the underlying storage and acceleration, we have used SmartSSDs. After creating the pools and the volume, ZFS gives us an option of setting the record size and selecting the compression algorithm. We have used the default 128 KB block size or the record size as ZFS calls it, and the level 1 GZIP compression. We have used industry standard FIO2 to write the data to the pool. We have created 12 threads with an IO size of 10 gig per thread. FIO block size used was 4K with an IO depth of 32. We have also set the buffer compress percentage to 75 so that the FIO can generate the data which can be compressible. We have created multiple such test configurations, increasing the pools and the SmartSSDs. We have 4 SmartSSDs with 2 mirror pools, 8 SmartSSDs with the 4 mirror pools, 12 SmartSSDs with 6 mirror pools, and 16 SmartSSDs with 8 mirror pools. The FIO is run on all the pools simultaneously here to push the CPU utilization to its maximum. Now let's see how much of an advantage are we talking about with this offloading. We have compared the value proposition against the three parameters here: throughput, CPU resource utilization, and the system memory efficiency. Let's first see the throughput improvement. We have used FIO tool itself to record the IOPS. In case of multiple pools, we ran FIO on all the pools simultaneously, and we have recorded the IOPS from each FIO run and plotted the combined IOPS. On the x-axis, you can see that we have plotted against the number of smart SSDs. So the 2 smart SSDs here refers to 1 mirror pool, 4 refers to 2 mirror pools, and so on. We have done this for 3 scenarios. The one where there is no compression involved, which is the off case, the gray plot here. The second where the CPU resources are used for the compression, which is the red plot here. And the third where the compression tasks are offloaded to the FPGA, which is the smart SSD plot, the blue one here. Note that the algorithm used in both the compression on cases is the GZIP level 1. We can see that offloaded GZIP can give as much as the 2x improvement in the performance with a higher number of pools. And it is fair to say from the graph that offloading is as good as no compression in terms of throughput. The next is the CPU resource utilization. The aim was to minimize it so that the resources can be utilized elsewhere. Again, we have plotted this for all the cases from 1 SSD, 1 pool to 1 mirror pool to 8 mirror pools, using 16 SSDs in total. While FIO is being run, we used Linux MP-stat to record the CPU utilization. We have done the same for 3 scenarios again. We can see that almost 90% of the CPU resources are utilized with more pools. We can observe close to 55% decrease in the CPU utilization in case of offload. It's even lesser than the case where the compression is off, and that's because we have also offloaded the checksum computation. The value proposition is more visible as the number of pools increase. Along with the improvements in the throughput and CPU resource utilization, we have seen the improvement in the system memory efficiency. This improvement is solely due to the peer-to-peer data transfer. The memory bandwidth increases as the IOPS increases. As you can see in the plot, the ratio in the case of compression offload is at the lowest while achieving the same level of IOPS as that of the compression off case, as we saw in the previous throughput slide. This means that in the case of the compression offload, the host memory bandwidth is significantly lesser than that of the compression on CPU bandwidth, thus freeing up the host resources for other application usage. There are a host of other things that can be added to this in the future. I've listed some of them here, like offloading the compression for the read path, GZIP kernel that supports multiple levels, or adding the offload to RAID or deduplication features of ZFS. With this, I end my presentation, and please reach us with the questions that you may have through the chat box or our LinkedIn profiles. Thank you for taking time to go through our presentation. Please give us your feedback.